Hi there, this is Astrophysics. This is Surveying the Stars Lesson 9, and this is Evolution of Large Stars and Supernova. Right, so red supergiant. So if a star is greater than 4 solar masses, the core becomes hot enough to cause energy release through further fusion to form nuclei as heavy as iron in successive shells, which looks like this. So the heaviest element that's made in red supergiants is iron. If you think about the binding energy per nucleon graph, the peak where you go up with fusion on the left hand side, and it peaks at iron. So it's got the highest binding energy per nucleon. So it makes sense that iron is the most stable element and the heaviest element that can be made in this situation. So here's supergiant star Betelgeuse imaged in ultraviolet by the Hubble Space Telescope, subsequently enhanced by NASA. And the bright white spot, NASA scientists believe, is likely one of its poles. So as you can see, laid like an onion, hydrogen and helium, and it'll literally go through every element, iron in the centre. So the question is, how do we get produce elements heavier than iron? Because stars, essentially, the life cycle of a star, when stars die, they are, the factories for elements. That's where elements are made. Right, supernova. So a supernova can occur when the iron core of a supergiant is greater than approximately 1.4 solar masses. So in this case, the gravitational forces are so immense, they're too great for the repulsive force of the electron. So the gravitational force will overcome the electrostatic repulsion, and the electrons are forced to react with protons to form neutrons. So you get a proton plus an electron. Product is a neutron plus a neutrino, an electron neutrino. So the sudden collapse of the core occurs within a few seconds, and its density increases from normal atomic nuclear density to about 1 × 10⁻17 kilograms per cubic meter. So the core suddenly becomes rigid. Obviously at that density it would be rigid. Collapsing matter surrounding the core hits it, obviously because the centre of it's incredibly dense. Everything else is getting pulled in by the gravitational field, and it rebounds with a shock wave, propelling the surrounding matter outwards into space in an outrageously large cataclysmic explosion called a supernova. So this is the Crab Nebula, which is the remnant of a supernova, which was observed all the way back in 1054. So the exploding star, so this is if something supernovas, releases so much energy that it can outshine an entire galaxy. So you've got one supernova outshining between 200 to 400 million stars. So a supernova is typically 1,000 million times more luminous than the sun. Within 24 hours, its absolute magnitude will reach between -15 and -20, compared to the absolute magnitude of the sun, which is 4.83. So elements heavier than iron are formed via nuclear fusion in the supernova explosion. The existence of elements on Earth that are more dense than iron, so periodic table, anything after iron, is clear evidence that the solar system was formed from the remnants of a supernova, such as just like the Crab Nebula in the image above. Right, so let's look at types of supernova. So we've got different types of supernova. So we've got 1A, 1B, 1C, and type 2. Now on the AQA specification, the one that it typically talks about is 1A. So spectrum, there's no hydrogen lines, strong silicon line, light output will decrease steadily, and the origin is a white dwarf, attracts matter and explodes. So that seems a bit strange. So type 1A supernova occur in binary systems, which is where we've got 2 stars orbiting one another, in which one of the stars is a white dwarf. The other star can be anything from a giant star or even a smaller white dwarf. So physically, the white dwarfs they've got low rotational speeds, are typically below 1.44 solar masses. If they go beyond this critical mass, what happens is they reignite and in some cases trigger a type 1A supernova explosion. So essentially the white dwarf can gradually accrete mass from its binary companion, or it could completely merge with a secondary white dwarf. So basically what happens is, if it accretes enough mass and goes above 1.44 solar masses, within a few seconds you get within the initiation of nuclear fusion, you get a substantial fraction of the matter within the white dwarf will undergo a runaway fusion reaction, and it releases outrageous amounts of energy to the order of power of 44 joules, and it'll unbind the star and detonate in a supernova explosion. Now, type 1a are useful because they produce a fairly consistent peak luminosity. So like if you did a graph of this, say, and you went luminosity against time, the luminosity will stay relatively constant for a long time. Because of that, we can use them as something called standard candles, which we're going to look at in a minute. By a minute, I mean right now. Right, so supernova are standard candles. So these are type 1a supernovas. So they have a known peak luminosity, and it allows us to, if we can see, a type 1a supernova, we can use it as kind of a guidepost for distances throughout the universe. So at their peak, these supernovae have an absolute magnitude of about minus 19.3. So by noting their apparent magnitude, how bright they appear to be from Earth, we can use that information to determine the distances to galaxies using the logarithmic equation which we've been using previously. So n minus m equals 5 log base 10 d over 10. And what we're going to finish with is a question, a standard candle question. So if you want to attempt this one, and then I'll talk you through it. So in a distant galaxy, type 1a supernova is observed to have an apparent magnitude of +8. So what we're going to do is assume that the type 1a supernova has an absolute magnitude of minus 19, and then we can calculate the distance to it. So apparent magnitude minus absolute magnitude is equal to 5 log base 10 d over 10. So let's put some numbers in. So we've got apparent magnitude of 8 minus 19, so plus 19, equals 5 log base 10 d over 10. So we're going to divide by 5 on the left hand side. So 8 plus 19 over 5 gives us 5.4. So 5.4 equals log base 10 d over 10. Then what we need to do is do the anti-log. So that's shift log on your calculator. So that'll give us 10. 5.4 to the power 5.4 equals d over 10. So to get the distance d, we need to do on the left what's on the left and then times it by 10. So that gives us distance d, and remember distance is always in parsecs with this equation, 2.51 million, or times 10 to the power 6 parsecs. And then really straightforward, convert that to light years, 2.51 times 10 to the 6, and there's 3.26 light years in a parsec. So that gives us 8.2 times 10 to the power 6 light years, or 8.2 million light years. Hopefully you found that useful. Thanks for watching.